Welcome to the Podkey summary of optimized custom machine learning operations with metal tensors from WWDC 2026. A lot of this week's Apple graphics and AI story really comes down to one idea: getting more model work closer to the hardware, with less fuss for developers. The big pieces are the M5's new neural accelerator inside each shader core, broader quantized tensor support in TensorOps, and a pretty practical path for building things like FlashAttention and dropping them into real models. It's fairly technical stuff, but the throughline is simple enough: faster inference, less wasted memory movement, and fewer awkward hand-built code paths. The headline on the M5 family is a dedicated neural accelerator block embedded in each shader core. That matters for dense compute-heavy jobs, especially the pre-fill stage of large language models, where you want raw throughput and you don't want the general-purpose GPU pipeline doing all the lifting alone. Apple's pitch here is that TensorOps can automatically detect and use that accelerator, so developers don't have to write one path for older Apple silicon and another for the new hotness. That's probably one of the more important practical points in all of this, because the best hardware feature in the world gets a lot less exciting if using it means maintaining a small museum of special cases. TensorOps also now natively handles 4-bit and 8-bit integer tensors in macOS and iOS 26. Then in the next release, version 27, Apple says it's adding 4-bit and 8-bit floating point plus 2-bit integer types, which really expands the menu for model compression. In plain language, quantization is about storing weights and activations in smaller formats, so models use less memory and often run faster. The nice part is how TensorOps presents it. You specify a quantized data type in the tensor descriptor, and the framework handles routing the work through available hardware acceleration. So in many cases, you're not manually dequantizing everything just to get the math done, which is exactly the kind of hidden plumbing developers are happy to never think about again. In macOS and iOS 27, Apple is also adding what it calls a scale plane inside a single MTL tensor. This uses FP8E8M0 scaling factors stored blockwise, with one scale value shared across each block of 32 data elements. If you work with quantized data, that's useful because the raw compact values usually need scale information to mean anything. Instead of keeping the data over here and the scales somewhere else and the metadata in a third place where it will absolutely hide from you at the worst possible moment, the tensor can carry all of that together. The scale plane gets its own descriptor with its data type and block factors, then attaches to the main tensor descriptor, so the whole package travels as one object. Another key concept here is cooperative tensors. Instead of bouncing intermediate results out to thread group memory, cooperative tensors spread their storage across thread private registers, so threads in a SIMD group can share data more directly. That reduces load and store overhead, which is one of those dry phrases that really means stop wasting time moving numbers around when you could be doing actual math. There is a catch, though. If you want to reuse a cooperative tensor as the input to a later matrix multiply, you have to check whether the layout is compatible by calling as _compatible as _input or as _compatible as input. If it isn't compatible, you have to materialize the tensor in thread group memory first. So the speed up is real, but not magic. You still have to respect the layout rules. This all gets very concrete in the FlashAttention example. FlashAttention folds the Q times K multiply the softmax and the final multiply by V into one kernel, which helps reduce memory movement and keeps the whole attention step tighter and faster. TensorOps supports that by mapping each SIMD group to complete rows of the intermediate matrix using execution_SIMD group scope. The intermediate QK matrix itself lives in cooperative tensors, which is exactly where that register-level sharing becomes useful. For the softmax part, TensorOps uses reduce_rows to get the per-row maximums, then map_iterator lines. Those reduction results back up with the original tensor layout before continuing. So this isn't just Apple saying in theory, you can do modern attention efficiently. They're showing the ingredients for a fused implementation that matches how people actually want to build these kernels. The other encouraging piece is that this isn't walled off as a neat demo with nowhere to go. Core AI lets Python developers register a custom metal kernel through Torch Metal Kernel and replace a framework's default attention implementation. That means a TensorOps-based kernel can slot into a PyTorch-derived model without turning the whole workflow into a science project. The example shown uses the SAM3 segmentation model. Export the PyTorch model as a Core AI asset, swap in the custom FlashAttention kernel, and it runs end-to-end while still producing the correct segmentation masks. That last part matters. Performance demos are nice, but correctness is the part that lets you sleep at night. There's also a pretty honest discussion here about what happens when TensorOps can't directly consume some custom quantized format. The recommended fallback is to load quantized chunks, dequantize them into F16 and thread group memory, and then pass them along as inline thread group tensors. That works, but it adds memory traffic, so you're paying for the convenience. The faster option is to dequantize straight into thread registers through a cooperative tensor, skipping that intermediate thread group storage. That can cut latency, but now you're back in the land of layout compatibility and careful handling. So the gain comes with more responsibility, which is a pretty common theme in performance work. The hardware gives you a better path, but only if you drive it like you mean it. So the overall picture is Apple tightening the loop between model code, quantized data, and the GPU hardware that actually runs it. For developers, the attractive part is not just more speed on paper, but better defaults and a clearer path from custom kernel to working app. And honestly, any week where the phrase scale plane starts sounding practical has been a very specific kind of week. This episode was generated by Podkey. Create your own at podkey.fm.
Podkey.